In this section, we're going to be working with increasing and decreasing functions, and to give a very informal definition at the top, we say a function is increasing informally. Obviously, if you're going basically uphill, kind of picture a roller coaster. When it's on its way up, we call the function increasing. We call it decreasing when we're on the way down. And so we'd say we're decreasing when we're going downhill. That's not a formal definition. We'll give a more formal one involving calculus notation on the next page. But what I'd like you to do is go down here and let's look at this purple function. Let's suppose that this purple function is the graph of some function that we call f of x. And right over here in red, I've got a tangent line to f of x hitting the curve right about here. And remember, when we're talking about tangent lines, we're talking about derivatives. So I'd like to analyze the derivative of the graph as I travel along the roller coaster. So you'll notice I'm going uphill. So I've got a positive slope, or positive slope of the tangent line. Right here, I have a slope of 0. I have a horizontal tangent. Then when I'm going downhill, my tangent lines have slopes that are negative. When I hit here again, the slope of my tangent line is 0 once again, and then when I'm on my way up, the slopes of the tangent lines are positive, increasingly more so as I go steeper and steeper uphill. But what these signs are representing is the slope of the tangent lines, and what I like to do with those is I like to make what I call a derivative sign chart, and we'll make those more in a little bit. But the first thing we do is we look at where the slope of the tangent line was 0. In this case, on this graph, that appears to be happening at about, I don't know, 0.8-ish, 1.8, and at about 0.2. My slope, or my tangent lines were horizontal, so the slopes were 0. Over here on this side of the graph, I was going uphill, so my slopes were positive. I was downhill, so my slopes were negative, and I was positive over here. And what I'm going to do is I'm going to also draw the graph of the derivative, which we did in the chapter 2, so you're fairly familiar with it. But remember, when I'm graphing the derivative, I'm really graphing the slopes. And my y values, because that's what this means, on my graph for the derivative represents the slopes of the original graph. And in the first region, the slopes were positive, and way down here, they're very positive. What that means is my derivative graph comes in from way on the top up here. You could maybe even say that the slope of this looks like it's about 10, which means I'm at about -1, 10. And what happens is, although my slopes are continuing to be positive, they're getting less and less so. So what happens is, and again, the slope is 0 right here, what happens is I end up heading like this. Now, in this whole region of the graph, my slopes were negative. The function was going downhill. You'll notice that it was its most downhill about right here. That's where it's about the steepest. What that means is that's where my derivative graph is going to bottom out. Okay, right about there. I'm still saying that the derivatives are negative in here because I'm still beneath the x-axis. And then it's 0 again right here, and then they're positive, increasingly more so. So I have this kind of parabolic graph of the derivative, which makes sense because mathematically when we take derivatives, the degree gets knocked down. And this original one looks like it was probably the graph of something cubed, which means when I drop that power down one for the derivative, I'm probably going to get something squared or more of a parabolic shape. You'll kind of notice that they kind of flow against each other. This one comes in from above while the original was coming in from below. And so what we're going to use on the next page is that concept to actually give formal definitions of increasing and decreasing functions. So what happens is, what this is saying is that when the derivative is positive, then the original function was increasing, which makes sense because if the slopes of the tangent line are positive, you must have been going uphill. If the derivative is negative, then the function had to have been decreasing in that interval. Again, that makes sense because slopes of the tangent line, when you're going downhill, those would be negative. If the derivative equals 0, what does that mean? It means that over that interval, f of x is constant. You might say, well, what in the world does that mean? Well, let's give a good example of that over here, just so you can see it. So let's make a fake graph. I'm going downhill, downhill, downhill. Then I'm going to curve, I'm going to come up, I'm going to go up, up, up. Maybe I'll make another little dip like this. Then maybe I'll go like that. And you'll notice right here, my slope is 0. And then when I'm going downhill, slopes are negative, 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 negative. Slope is again 0. Now they're positive, 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 positive. And maybe slightly 0 in here. Right here, though, is a constant slope of 0. So that's what this is saying. The definition of increasing and decreasing allows the endpoints to be included in the intervals under consideration. Also, though some books don't. All they're saying is if you wanted to say if this was at A and this was at B, some books say that it's decreasing between A and B. Some books say that we don't leave them in. It really does not matter to me. I'm not too picky on that. I actually usually leave them open because I consider it kind of 0 at A. So I like to leave them open. So down on the bottom, you don't have colors, so if you have the highlighter, that would be great, so you know which function was red and which one was blue. And at the original function, you can kind of tell based on just the curvature. This is the blue function, okay? And over here is where we have the graph of the derivative. And let's discuss why the graph of the derivative looks like this. And again, to repeat, it's because we're graphing, that red graph is the slope of the tangent line. So it's graphing all these derivatives, which are very steep and positive up here, which is why that red one comes in from way up above. And it's 0 right here, and then again, they're still positive. So this would be the original with the derivative. On the next graph, my original function is the parabola, and we discussed last chapter how the derivative of those graphs are lines. And so you'll see that everywhere down here, the slope of the tangent line is negative because these tangent lines are going downhill, so their slopes are negative. Hence, my derivative graph comes from the negative direction. Right here is where the slope of the tangent line is 0, which is why I'm hitting 0, 0. And then they go positive. Now we've done these before, so I'm not going to talk about those too much. I tested you on that in chapter 2 already. So now what we have is some guidelines for finding, without looking at a graph, the intervals on which a function is increasing or decreasing. It all depends upon the derivatives. Well, the first thing you need to do is you need to see where the turning points or where the critical values are of f. So what you do is you first determine the critical values. So we need to circle that and remind ourselves how we find critical values. Critical values meet one of two criteria. They either make the derivative equal to 0 or where the derivative does not exist. So let's write that. This is where the derivative, and sometimes we'll write that as f prime of c, equals 0, or where the derivative there does not exist. Those are what we in section 3.1 said what critical values are. So the first thing we do to determine increasing and decreasing is we go locate all of our critical values. And then we determine the sign of the derivatives, meaning positive versus negative, in each of the intervals that it chops up. If we say that the derivative is positive in an interval, then we know the original function was going uphill, or the roller coaster was climbing. If the derivative is negative, then we know we were going downhill, or the original function was decreasing. If the derivative was 0, it's actually a little inconclusive. So let's go take a look at what this next thing says. We say a function is strictly monotonic on an interval if it's either increasing the whole way or decreasing the whole way. That would be kind of like when you get on a slide or on a ski hill and you just go down. We would call that monotonic because you're going down the whole time. Even if you kind of go down and you plateau for a little bit and continue to go down, we would call that a monotonic function because it's going down constantly. So, if the derivative is equal to 0, it does not necessarily mean that you're going to have a change from increasing to decreasing. Let me show you an example of that. Right here, I have a tangent line which is horizontal. So right here at 0, I know that the derivative at 0 is equal to 0, which means 0 is classified as a critical value. However, when I look to the left of the critical value, the hill or the function is going uphill. When I look to the right, it continues to go uphill. So this function is increasing on the entire interval, and so there is no change. So it says, note, if the derivative is 0, like it was right here, it doesn't mean that it's going to change from increasing to decreasing. which is why it's going to be important that we test each interval when we start running tests, because you can kind of see what's going to happen. If we want to figure out where a function reaches a maximum, a relative maximum, if we knew it was increasing, then it was 0, and then it was decreasing, I know I hit a maximum. If it was increasing, then it was 0 and still increasing, then I actually know I hit what's called, some people call that a saddle point, or where it plateaus for a little while. But notice that the fact that I had a critical value does not guarantee that I've changed from increasing to decreasing. So it says find the open intervals for which this function is increasing or decreasing. So the first thing we need to do is find our critical values, or our critical numbers, whatever you want to call that. Remember, what we do for that is we say, well, where is the derivative equal to 0? So first thing we do is use our power rule to take the derivative. So there's my derivative function using the power rule. I want to know where is my derivative equal to 0. So what I'm going to do now is factor, which usually is what happens for our polynomial functions. I have two places on the original graph, or two critical numbers, where the derivative is 0. And the book tests them in a chart like this. I'm not a real big fan of the chart, and I'll tell you why. I think it's easier if you take the information that would be on the chart and if you lay it out on what I call a derivative sign line. But let's go take a look here. I've got my intervals, all right? I know my critical numbers are at 4 and at 0, because that's what makes the derivative equal to 0. And there's no places where the derivative doesn't exist. So let's go take a look. I want to see what's happening with my derivative on different parts of the graph. So I like to call this negative infinity and this infinity. I know at these places it's 0, but now what I'm going to do is test. And again, some people say, well, if I get a positive for the first one, doesn't it just go positive, negative, positive, negative? Not always, because just like this one went positive, 0, positive. So you do need to test these before you just assume what's going to happen. So to test them, what I do is I take a value in this interval. And let's pretend we're going to think of in that interval -1. What I do is I plug that -1 into my derivative function. And it's easiest to put it where you factored it, because you're just doing a sign analysis. So when x is equal to -1, I'd have a negative times a negative, which is positive. In this interval, I probably maybe test the number 2. And when I plug a 2 into the original function, I'd have a positive times a negative. Likewise, when I plug maybe a 6 in, I'd have a positive. So what that tells me, since I'm going positive, negative, positive, again, I like this layout of it a lot better. I know that my conclusion is that I'm increasing from negative infinity to 0, which is right here. Okay, and then the function must have been decreasing between 0 and 4, because the slopes of the tangent lines were negative, meaning it's going downhill, and then it was increasing again from 4 to infinity. But I think the information on this whole chart is better laid out with a sign line. All right, and then down here is the graph of the function. So you can see, I'm almost out of time, I'm going to have to go to another video here in a little bit. But you can see that when I zoomed in and graphed this and screenshot it for you, here are the places where the slope of the tangent line is 0. You'll notice they occur at 0 and it occurs at 4. Those were called my critical values, or my critical points. I then ran a test in each of the intervals, and I found that one thing over here made it positive, then it all does, because you can't change from positive to negative without having a 0 in there. And I already have found my 2 zeros. So this was going uphill because it's positive. You can see this is going downhill, negative, and then this is going uphill. So from negative infinity to 0, it was increasing. From 0 to 4, it was decreasing. And from 4 to infinity, increasing again. So you might say, well, why can't I just look at the graph? The reason for that is you won't have your graphing calculator. You have to use calculus and derivatives to determine where a function is increasing or decreasing. So I will do another video for the rest of 3.1, and I'll be back in a minute.